Hello, we are here for one more lesson of this T-Flex CAM training course, and the topic for today will be still the 3D milling with the specific topic of milling a surface of revolution. So to create a toolpath of a surface of revolution, we have a special function, and this is one example that I've prepared to show what we mean about this. So the idea in this particular example is to mill this small area here that you can see sits on this surface of revolution. It's not a planar element, it's cylindrical, has the same center that this cylinder that we recognize as being the part. This is not very complex, and the idea in here this is a 3D milling, a 3-axis milling. So what we will obtain, it is a rotation part, and the axis of the tool will remain on the same position. Let's try to create something and see the parameters for so. So the idea, it is again CNC menu, boundary 3D milling, and continuing down on these options we have this function called rotation surface milling. So we can select this in several ways, but we need to choose our solid, so all of it, and I can continue this basically if I select simply the face that I want to mill. So this one, okay? The face recognizes this internal island, so it is okay. And now moving to the parameters, they are very known from you at this point. So I will call a tool file. I will choose one tool. Let us see what it is. So it's 8 mil diameter with 1 mil radius. Work feed rates on rapids, the allowance, cooler, spindle rotations and directions, so nothing in particular. The pass type, we have all of these types that we know already, and I will use in this particular case the spirals because they are very suitable for this case. So any of this one, so outward spiral. Increment, I will say in this particular case 30. Step of passes, I will say half of the tool, so 4 mil. And I will not say anything else, so simply calculate it, and okay, here it is, a very nice toolpath that we will simulate. And as you can see, the tool, it is changing the axis, but what will happen, it is in the machine, it is the part that will move. So seeing more parameters for this particular case, we can work with the thickness also, starting for example with 5 until 0 with 1 mil step. We can insert a side offset, so for example 2, and as you can see we've done increments, and all the toolpath went a little to the inside due to the side offset. I will put 0 again. Okay. What else? I have a filter here also that allow me to filter my islands. So if I say all, okay, it will respect what is inside. If I say only external, it will calculate, but it will ignore the internal island. which is a nice feature because allows us to be very flexible. Cylindrical surface, we need to leave this selected because this is for every time we are working in this kind of surface, so it's a must. This is the direction, passing or counter, and the reflect will create the toolpath from the inside because it's the opposite direction, what in this case it's not interesting. Plunge machining, you know already what it is, and these additional parameters, again, it will calculate the toolpath in areas where the system thinks it was not possible to mill. I'm not sure if we are able to do something in this particular case. Probably too big. Let us give a little smaller. Okay, and now it already calculated as only this area has having some material. Besides, we still have, take this out, we still have the precision that you know already. In this particular case there is no circle interpolation because the movement is it's a little different, and we can connect this also to rotation of the axis, but maybe it will make more complex toolpath, so it's we need to use this careful, and we need to have the post-processor also properly defined to take advantage of these rotations. So for this particular type of toolpath, this is quite easy. The parameters are very similar to the ones we've seen already in the whole previous tool types. So I hope this easy example it's enough to explain the concept of how to use this surface of revolution milling.